Oh, good morning. My name's Tom Shire from the University of Glasgow's Computational Engineering Centre, and I'm going to talk about the use of discrete element modelling and wave structure interaction. I'll start by introducing discrete element modelling and then how DM can be coupled with computational fluid dynamics, and I will then briefly mention what I believe are the main areas of application for DAM-CFD in wave structure interaction, although if there's any other areas, I would be delighted to know of them. So DEM models individual grains or particles as rigid bodies. These grains can be anything from 100 microns, so fine sand, up to the kilometre scale. DEM is very computationally expensive, and so its use has increased as computers have become more powerful in recent decades. In geotechnical engineering, DEM is normally used to study the fundamental mechanisms underlying engineering problems rather than for routine analysis. This is because it allows microscale mechanisms to be observed in a way which cannot be achieved with continuum analysis or lab testing, but also because of the computational expense. The drawback of DEM is that particles are often idealized as spherical, which can affect the realism of their interactions. However, a huge advantage is that in DEM, we can easily measure variables which experimentalists cannot, such as interparticle forces and stresses and void geometry. The basis of DEM is that each particle can move in space and overlap with other particles where they contact. The reaction force at contact points is related to this overlap via a constitutive law. The resultant force on each particle is then used to calculate the acceleration, velocity, and displacement for each particle at a given time step. DM has also been widely coupled with CFD for a number of engineering applications, in particular in industrial processes, such as pharmaceuticals or material processing, soap powders, and in geotechnics. My work using coupled DM-CFD has been carried out mainly in the context of internal erosion of dams, where seepage through an embankment causes fine soil particles to be washed out, leading to eventual collapse of the dam. The most common form of DM-CFD coupling, and the type that I have predominantly used, involves overlaying a coarse mesh, so coarse meaning just larger, much larger than the soil particles, on the particle domain, and the mesh is then used for finite volume CFD. Coupling between DM and CFD takes the form of fluid particle interaction. The mesh is used for two purposes. Firstly, to solve the CFD, and secondly, to calculate spatial averages to exchange between DM and CFD. Fluid velocity and pressure terms are sent from CFD to DM, and locally averaged fluid particle interaction forces and porosities are sent the other way. The locally averaged terms are then added to a locally averaged Navier-Stokes equation, as shown here, which is solved on the CFD grid. So you can see the porosities and fluid particle interaction force terms are added. The great idealization of this method is that velocities are averaged within each fluid cell, which can contain hundreds or thousands of DM particles. This is clearly an idealization of reality as shown by the open foam simulation at the subparticle scale on the left here. But it is computationally efficient enough to allow a representative number of soil particles to be simulated. I'm very keen to explore the options for modelling wave particle interaction as part of CCP-WSI+. I won't go into the existing options, but I've listed a couple of recent attempts to model this here. Finally, I think the most interesting area of application for using DM to study wave structure interaction is in coastal defences, breakwaters and other areas where wave scour is important. Another area is the highly destructive debris flows which frequently occur in mountainous areas. But if any other areas where DM could be used to better understand fundamental mechanics of wave structure interaction problems exist, I would be very happy to discuss it. So that's the end of my talk, and thank you for listening.